Okay, so as Julie said, I was part of a cohort last year, basically the same um, program as you guys are in. So yeah, I think for context, I'm going to give you just a very quick overview of what I do and where I work. I think it's kind of important just to understand where I'm coming from. So I would describe myself as primarily a level 1 or level 2 algorithm scientist. I work with a lot of different satellite instruments from NASA, NOAA, ESA. So because I'm like at the L1, L2 level, my data comes in like sensor swaths, right? So each granule of data, it's sort of some arbitrary polygon on Earth. I don't really deal with level 3 or model data too much. So that's like, kind of cubes of data where you have lat long time. I'm primarily a Python ecosystem workflow person. So, here's kind of the typical packages I use on a day-to-day basis. Like that's probably familiar to you if you're a Python user. And so, where I've worked, I'm now at the University of Michigan. I'm actually a kind of recent transplant here, like 2.5 years ago. Before that, I was at the University of Wisconsin. So that's where I basically spent my career as like a PhD level scientist at those two places. So, for context, those are both large, well-resourced researched institutions. So that does sort of, I guess, color my experiences with computing to some degree. And there's a lot of shared computing resources. And, what will become important later is there is like an institutional Amazon Web Services account that I have access to. Okay, and then I thought it would help to just kind of have an overall kind of landscape of how I see the different scales of computing that I use. And so again, this is a bit sort of colored or flavored by where I work. So, in the lower left-hand corner, this is like scales of problems that you can do on your laptop or desktop, right? Kind of small in compute time or data size. But then, I'm in research groups that have shared like Linux servers. These are usually like pretty big machines, so maybe like tens of terabytes and, multi-processor kind of things. But then I also have access to like a shared compute cluster. So this would be like a high throughput or high performance computer. So that's, like hundreds or thousands of nodes, but maybe not so much data storage. But then I put cloud computing kind of out here to the right because for my workflows, I actually don't really see it replacing any of these other things. It's really like I see it as a new capability that's allowing me to do analyses on these big data sets that would have been hard to do on any of these other machines. And that's kind of what I um, just stated here, particularly with NASA Earth Data Cloud. That's kind of like what I'm leveraging out here with cloud computing. So my experiences, like say a year ago before, or maybe a little more than a year ago before joining up with the NASA Openscapes group, I basically had, I would say, zero useful experience. I had like a number of sort of small and I would say kind of negative experiences. These are some of kind of a handful of things I tried like in the previous year. One was just talking to some cloud engineers or IT at my institution. So I'll say like both UW and University of Michigan, they have pretty great IT support. And like there were cloud engineers where I could just book a time and talk to one for an hour just about cloud computing. But I tried that, but like after the hour, it was like really hard to say, all right, how is that going to be useful to me? It was really not very clear. I actually went to a webinar offered by Amazon Web Services, some actual staff engineers. Briefly, that was useless. Again, after the hour, it was like, I don't really understand like how I'm going to use that in my workflow at all. Costs always seemed very mysterious and kind of didn't seem that inexpensive, actually. When I sort of looked at the cost tables, it really seemed like this wasn't going to be that inexpensive. And, maybe we'll kind of come back to that point later. And I say a lot of material, like if you just kind of search for doing cloud computing with like earth science data, I feel like a lot of it is geared toward model analyses. And I think part of that is, the climate model analysis groups, they sort of by necessity, I think, are farther along. And so there's a lot, if you just kind of look for tutorials, you sort of find their stuff. But it's not always obvious how one would adapt that to like satellite data that's not gridded in the same way. And kind of related to that, a lot of that required sort of specialized Python packages and or data formats. So again, it was not very obvious like how to adapt to what I do as like a L1, L2 satellite data scientist. And kind of stressing a lot of these conversations, like particularly with like cloud engineers or like the Amazon Web Service webinar, it was really just talking about like administration of cloud services. So it's like, well, yeah, I went to this webinar. They told me how to like create a Kubernetes cluster on Amazon, and that's great, but like I don't know how I use that. Um, so there was kind of like a disconnect for like what was out there and what I kind of needed to the like material or instruction I needed. So okay, now today, like after Openscapes, NASA Openscapes, and particularly learning coiled, it's very easy for me to run code in the cloud with like little extra overhead. It doesn't really require any other specialized Python packages. Now, coiled is a Python package, but like I didn't have to, um, learn any other numerical packages like to do the actual analysis. I can just do the same thing I always do, and it doesn't like require a cloud optimized data format. And I think this is actually pretty important because most of the NASA satellite data is just going to be in like NetCDF or HDF5, and that's not really like the cloud optimized data format you want if you kind of look at, if you just kind of sort of, again, search for like climate data in the cloud, they're probably going to sort of aim you toward like a cloud optimized, not like a NetCDF type thing. So the key thing is I really didn't have to modify my workflow. It's just you kind of add this wrinkle on top with coiled that just allows you to deploy it when you need to. Okay, and then just briefly, like the opportunities that you'll get in as part of NASA Openscapes. Now, I don't want to. It kind of skipped over Jupyter hubs. I don't want to like lessen those. I think those are very powerful as well because they're extremely easy to use, particularly if you already use Jupyter. It's basically the same thing. It's just your compute kernel is running in the cloud. So it's kind of good to get your kind of toes in the water and very helpful just to prototype and do like efficiency checks to see how things work when it's running on cloud hardware, because there are some small differences. The issue with that is like wasn't a straightforward way to transition that kind of back home to the work I do at my own institution. Um, I'm not aware of anyone at the moment like administering a similar setup like in my department here. And I think this is, at least at the moment, seems like a big lift to try to figure out how to do myself. But coiled, on the other hand, like I said, very easy to use, extremely easy to transition to my workflow, and there's like essentially zero administrative overhead. Okay, so one thing I think is helpful to think about as you go through this process in the NASA Openscapes group is just how to proceed with like what you learn here and how do you sort of carry that home with you. And so my recommendation is identify a near-term task that you can shift to cloud processing. And this task ideally, I think, should have like these three characteristics. And the first one's probably the most important. I think it should be something you need to do anyway. You don't necessarily want to pick a, random new task that was sort of aspirational because it'll just be hard for you to prioritize to spend the time to really like learn the tools. So if you pick something that you were going to do anyway, that kind of automatically happens, right? Now, of course, pick something that is uses the data set that's in the cloud. So as long as, if it's NASA satellite data, it's likely already part of Earth Data Cloud, or NOAA has like quite a number of open data sets as well from their satellites. And then third, like, it's probably good to pick something like large-ish so that you'll get some immediate benefit. If you pick something too small that you could have done on your laptop anyway, then I think you'll be like less excited about it. But if you pick something big that's like, oh yeah, that would have been really hard to do, but this made it really fast and really easy, I think you'll get a lot more excited about it moving forward. So what I'm gonna next go through is just here like a use case of this was exactly what I did. I picked a task that fit these three criteria, and it was basically the analysis I wanted to do for my AGU poster. Okay, so I want to do like a very brief scientific background on like what I was doing, just to kind of give you some context. So this is what I would say is like a kind of L1 data analysis task. And the background here is that satellite instruments often have sensor arrays. So that means there's an array of physically different detectors. And those will have like, their own unique set of calibrations. So there's a challenge there to make sure, all the detector elements basically agree and that their calibrations are consistent. So how do we track that on orbit? So one way to do that for a visible or near eye sensor is look at the top of deep convective clouds. So on the right, I have just a picture from like a MODIS true color. So, this white blob in the center is basically just looking at the top of a deep convective cloud. So you can notice that they're, very homogeneous and very sort of uniform in their brightness. And so they're kind of a useful, like, standard calibration target. Okay, so the problem is I want to apply that technique to data from the NASA Orbiting Carbon Observatory, so OCO. The issue with this is, of course, you don't know a priori when and where these are going to occur. So you can't do some simple subsetting, like say here, go through this lat long time box and extract that subset. I really do need to sort of trawl through the entire data set and then interrogate it based on various variables in the data set, and including some of the level 2 retrieval products. And that will identify, the specific locations and time when these occur. But of course, since I need to sort of trawl through all the data, if I want to do the whole thing, it's roughly 12 terabytes a year, 13 years of data. So it's like roughly 150 terabytes total size for that data set. The output data will be pretty small. It's like something on the order of like 4 gigabytes. So in the old workflow, right, we'd have to download all of that. It's too big to fit on my group server. So already it becomes awkward, right? Well, maybe we could do the process in stages, like maybe do it 1 year at a time, and then delete that year and then download year 2, et cetera. Like that would work, but that's a lot of kind of tedious manual management of that data flow, right? And assuming like 50 megabytes per second download, which is what I typically get to the DAC, that's like 36 days straight. Okay, but now the new option is use Coil to do this and then run it directly in AWS in the Elastic Cloud where the data resides. So it turns out, because this is mainly like a subsetting and then just some simple math with that, we don't really need big expensive Amazon Elastic Cloud hardware. We can basically get Matt Rockland's rule of thumb here that if you're in this case, it's roughly only going to cost you 10 cents per terabyte to process this. There's some assumptions here that your code is like reasonably optimized and that you're using kind of the small CPUs. The details of this aren't unimportant now, but just keep this in mind that you can do this like quite cheaply. So this rule of thumb says that it would cost maybe $15. So how did it go? I would say really smoothly. You don't have to understand that like the science impact of what I did, but I just showed a couple plots here that say, yeah, this worked. And here was like the number of deep convective clouds I identified over the whole records for OCO 2 and 3. So this was basically, 13 or 14 sensor years of data. And then here was like the radiometric offsets that I saw between the detectors. Okay, so then to kind of wrap up in the next few slides, so I'd say the key points or sort of lessons learned from this process is, if you develop in a mode where you develop the code on a small sample data set that fits on your local machine. So like in my case, I basically just downloaded one day of the 13 years, developed and tested with that. Once you're done, then with Coiled, you can basically just deploy that same set of code to AWS for the production run. It wound up being kind of easiest to chunk it into 1 year of data at a time. And I would spin up 100 EC2 instances and run them in parallel. And each year takes about 30 minutes to process and costs less than $1. And one of the nice things with Coil, there's this web dashboard that kind of gives you immediate feedback about how things are running and how much they cost. So this is just a screen grab of a few of those jobs. So, again, here roughly half an hour and approximate cost like 80 cents. And then here is just a screen grab of like the cost explorer in my actual AWS account. So it ended up costing me like a bit less than $15, like, 10 to 12. Okay, so then kind of final thoughts on this. Like I will say, yeah, maybe going back to this a minute for a second. I will say like the costs are still opaque. Like I really don't understand like how it ultimately arrived at this number. I couldn't really explain that. But the real cost seems so much lower. I'm actually kind of not worried about that at all. And I think, I write a lot of like, NASA Rose's proposals and that kinds of thing. It would be very trivial to put like hundreds of dollars a year on a grant proposal like that just for cloud computing credits, and that'll go a really long way for these type of analyses. And I'll say that Coiled makes this much easier than I realized like a year ago. It really strips out the admin overhead. And then this sort of like test locally, deploy to AWS is like very easy to do that workflow. And then the third point is this sort of parallelism I really didn't appreciate till I did it myself. It really allows you to process data very fast. And just, what I bolded at the end is like, it really feels like a superpower for processing these satellite data sets. And it's really, I would say it's a new capability that's allowing new analyses and importantly, like fusion of multiple satellite data records together. Like you could imagine if I wanted to combine two 150 terabyte data sets, like how much worse that would be. But with deployment to EC2, it's like very easy to think about attacking problems in that way.